Okay, welcome back. Now this time we're going to do a roller coaster kind of motion, and we're going to prove the equations of circular motion and do some interesting stuff with that. In physics we learned that when something is going around the circle, that in order for it to not fall off at the top, the minimum velocity it needs to have is the square root of rg. Okay? I'm not going to go through the derivation of that, but if you are interested to go to see the derivation of that, you can look at my video lectures on chapter 6 on circular motion, and I go through to derive on how and why the minimum velocity needs to be square root of rg. R is the radius of the circle that it's going around. So it needs to have minimum velocity of that. So my question now is, if a roller coaster is falling from a certain height, what should be the minimum height? Okay. What should be the minimum height? What should be the minimum height of the roller coaster so that it has enough velocity here so that it won't fall? Okay. So let's assume that friction is not doing a very significant amount of negative work. So let's assume it's negligible. Therefore, the potential energy that the object has up there is going to equal to the sum of the potential energy that it has here plus the kinetic energy that it has there. So this is potential energy initial, it equals potential energy final plus K final. Potential energy initial, mgh initial, potential energy final, mg times the diameter, I can say here. This is the distance from here to here is twice the radius, or the diameter, so twice the radius. And then plus the kinetic energy, half m v final squared. And then v final is the minimum velocity that it needs to have over there. Okay? So the mass and the mass and the mass cancels. So we have g times h initial equals 2gr plus half velocity squared. Velocity squared is rg. Okay? So g cancels. H initial equals twice r plus half r, which is 2.5 r. So according to that, if the friction can be ignored, the roller coaster must be started 2.5 times the radius. So let's now measure our radius here. Okay. Our diameter is 40 centimeters. Okay, 40 centimeters. So our radius is 20 centimeters in our case. Okay, so let's say 20 centimeters is our radius. Therefore, I need to start the object 2.5 times 20, which is going to be what? 50. So where would that take us? I'll put a little marker here. Like this. 10, 20, 30, 40. Right there is my 50 height marker. Okay, let's see if that will work. When it comes here, I don't want it falling. I want it to continue its path. Okay, it fell with 50. Okay, why? Well, one thing could be that friction wasn't negligible. Okay. Maybe there's some friction. The other reason is because this is a rolling object. Okay? So we'll do in a minute the calculation for the rolling object. Because it is a rolling object, part of its energy goes into rotating the object. And so you actually need to go up a little higher, okay? So potential energy initial equals potential final plus K final. mgh initial equals mg2r. This time I have two kinds of kinetic energy. Rolling, rotating, and translational. Okay, so we're going to have mgh initial 2mgr plus the moment of inertia of the solid sphere is 2/5 mr squared. And then omega squared is the angular velocity, the radial velocity. Okay? And so we have mgh initial 2mgr plus 2 and the 2 cancel. We have 1/5 mr squared omega squared plus 1/2 mv squared. Now how can we combine that? Well, we're going to argue that the object is going to experience pure rolling motion. For pure rolling motion, r omega is the same as the velocity. So therefore, this whole thing becomes velocity squared. So I can combine these two, which means I'm going to get uh, 7/10 mv squared. The v, the m and the m and the m cancel. V squared, I can still put square root of rg. So square that, you get rg. And then the g and the g and the g cancels. 2 plus 7/10 h initial must be minimum of what? So 20 plus 7, 27 over 10 times r, which means 2.7. Okay? So h initial is 2.7 r. What was the other one? The other one was 2.5 r. So it's telling you you have to start it up higher because part of its potential energy is being converted into rolling energy. Yeah. Okay, let's put the marker on 54. This one is going to be a little bit more doable, but it's probably still not going to work because of rolling friction. Because as it's rolling, the rolling friction is slowing it down. So let's try that now. Okay. You see, it still wasn't perfect. In ideal situation though, if you're really making a roller coaster, you would want to go even more faster than Vmin. Because you don't want the object to be barely on the verge of falling here. So you might want to make Vmin twice the square root of Rg. Okay? Just to make sure it has enough velocity there. Well, in that case, we're going to be much safer. Okay? So if we have 2 square root of Rg, you put here 2, you square that, you're going to get 4. So you're going to get a certain number like 4 times this 7/10, okay, which is going to be 28. Okay, so you're going to have 28 over 10, and then when you add 28 over 10 plus 2, you're going to get 20 and 20. 20 plus 20, that's 28, that's 48. 48 over 10 is 4.8. Now notice how safe that is, because now it's going to go fast enough over there for people not to fall off the roller coaster ride. So if it's 4.8 times the radius, if the radius is 20 times 4.8, it's going to be 96. centimeters. 4.8 times 20. Okay, 96 centimeters. Now watch. Goes way up there. 96 centimeters. Well, now it's going to have twice the minimum velocity that it should have over there. Plenty of velocity to not only just make it there, but go all the way, make it out here, and even go off the table. You see? So this the equations of circular motion, rolling motion, all of them combined, you can see how useful they are in making roller coasters and stuff like that. Thank you very much.